Hi, and welcome back to Tactical DevOps. I'm Joe.
And I'm Jane. Today we are taking a look at services and networking in Kubernetes.
So imagine it's like 2.0 a.m., a critical physical server in your data center just caught fire and completely died.
Oh, the classic nightmare scenario.
Right. And, in the old days of traditional infrastructure, your pager goes off, you're scrambling, you're logging into switches, and you are just generally panicking trying to manually reroute traffic.
Yeah, trying to bring a backup server online before the users notice.
Exactly. But in Kubernetes, the system barely even blinks. It notices the hardware failure, shrugs, and instantly spins up exact clones of your application pods on healthy nodes. It's a brilliant system for high availability, but it introduces a totally different kind of headache for you.
It really does, because those new pods, those clones that just saved you from a 2.0 a.m. outage, they do not inherit the network identity of the dead ones.
Right. They get completely new IP addresses.
Exactly.
Yeah.
They get fresh IPs from the pod network's CIDR block. The environment is fundamentally chaotic by design. Pods are mortal, They're ephemeral.
Very ephemeral.
Yeah, when a controller or like a replica set sees that desired state doesn't match reality, doesn't try to resuscitate a dead pod, it just deletes the record and provisions a new one from scratch.
Which creates a massive architectural problem when you're building a distributed system.
Oh, huge.
If your back-end database pods are constantly dying and being reborn with new IP addresses, how does your front-end web application ever know where to send its network traffic? It sounds like you would have to run a script every 30 seconds just to manually update configuration files.
Yeah, and that would defeat the entire purpose of automation.
Yeah.
Be incredibly fragile. So the solution, the abstraction layer that brings order to all this chaos, is the Kubernetes service.
Okay.
It acts as a stable, persistent anchor in a sea of changing infrastructure. When you create a service, you basically get a static IP address and a stable DNS name entry for a highly dynamic group of pods.
So we are completely decoupling the front-end clients from the back-end workloads, right?
Exactly. Decoupling is the magic word.
The front-end application no longer needs to track individual pods. It just talks to the service. And the service handles the heavy lifting of figuring out who is actually alive and ready to receive traffic at that exact millisecond.
Right. The front end just sends requests to that single service IP. The service sits in the middle, maintaining that stable identity, and it automatically load balances the incoming traffic down to whatever healthy pods are backing it.
Even if things are scaling up and down wildly?
Yeah, the pods can crash. They can scale up to 100 instances during a traffic spike, scale down to 2 overnight, or get shuffled around the cluster by the scheduler. The front end never knows and never cares. It is completely insulated from all that churn.
Well, the decoupling makes perfect sense conceptually, but the service still has to know who those backing pods are. If we aren't hard-coding IP addresses into the service either, how does it dynamically track these pods in real time?
So it relies on a core Kubernetes mechanism called labels and selectors.
Ah, okay.
Yeah, when you write the manifest for a pod, or more likely a deployment that manages those pods, you attach metadata tags to them. These are just simple key value pairs called labels.
Like what, for example?
So you might tag your backend pods with something like app.kubernetes.io/name equals my app, and maybe another label like environment equals production.
Oh, I see. Then the service is basically instructed to act like a search engine for those specific tags.
Exactly like a search engine.
You give the service a selector, like app.kubernetes.io/name equals my app, and it constantly watches the Kube API for any healthy pods carrying that exact label.
Yeah, it queries the Kube API continuously. Whenever it finds matching pods that pass their readiness probes, it compiles their current, constantly changing IP addresses into a dynamic list.
And that list is updated on the fly.
Instantly. In modern Kubernetes, this list is managed by an object called an endpoint slice. As pods spin up or die, the endpoint slice is automatically updated, and the service routes traffic based on that real-time list.
I love thinking about this mechanism like a busy restaurant. The line, cooks in the kitchen, are your pods.
Oh, that's a great analogy.
Right. So during a Friday night dinner rush, cooks are rotating, taking breaks, some are clocking out, new ones clocking in. The kitchen staff is constantly changing, but the order window, the place where the waiters drop off the food tickets, that is your service.
It stays bolted to the wall in the exact same spot.
Yes. The waiters, which represent your front-end application, they don't need a map of the kitchen. They just drop the ticket at the window and don't care whose name is on the chef's coat.
And to push that analogy even further, the specific burner on the stove that the cook is using to make the meal is your container port.
Oh, I like that.
Yeah, the waiter just drops the ticket at the service window, and the service automatically hands it off to an available cook to process on their specific burner.
Which naturally leads us to how you actually build this order window. Because, conceptualizing it is one thing, but looking at the code is where the rubber meets the road. What does the baseline configuration for this actually look like?
Well, we build it declaratively using YAML manifests, just like everything else in the ecosystem. And the most fundamental way to build this is using the absolute default service type, which we call a ClusterIP.
ClusterIP, I mean, the name sort of gives away its boundary.
It really does.
This is providing an internal IP address strictly for the cluster.
Yeah.
If I am sitting at a coffee shop on my laptop, I can't just open my web browser and hit a ClusterIP service directly, right?
No, absolutely not. It is completely isolated to the secure boundary of your Kubernetes environment. It is designed specifically for pod-to-pod communication.
So like an internal web front end talking to a user database?
Exactly, or an internal caching layer. To build it, you start with the standard APA version v1 in-kind service.
Sure.
Under the metadata block, you give a name, let's say my internal service. Then you define the spec block.
And inside that spec block, we define type cluster IP. Though I know if you omit the type field completely, Kubernetes will just default to cluster IP anyway.
Right, it's the implicit default.
But the critical piece is right below that, the selector. We indent and write app::myapp to tell the service which pods to claim.
Yeah, and then you have to define how the network traffic ports are handled. In the manifest, under the ports array, you have to specify a port field and a target port field.
Oh man, getting those two fields backward is basically a rite of passage.
Oh, tell me about it.
When I first started writing these manifests, the port mapping drove me crazy.
It is a very common stumbling block for sure. The rule of thumb to remember is that the port field, let's say we set it to 80, is the port that the service itself is listening on. This is the order window.
Right.
The target port, let's say we set it to 8080, is the actual physical port that your application container is actively listening on inside the pod.
Okay, so traffic hits the service on a clean, standard port 80. The service seamlessly translates that request and forwards it to the pod on port 8080. But I have seen this go horribly wrong in practice.
Oh yeah, what happened?
A developer decides to update their Spring Boot application to listen on a new port, say 9000 instead of 8080. They update their deployment manifest, but they completely forget to update the target port in the service manifest.
Oh, yep. That creates a classic silent failure.
It's the worst kind of failure.
It really is. The service is happily accepting traffic on port 80, and it's dutifully forwarding it to the pods on port 8080. But the pods are now listening on 9000.
So the traffic just drops into a black hole.
Exactly. The pods show as healthy, the service shows as healthy, but the connection just times out. It highlights why the decoupling is powerful, but also why you must keep the deployment and the service aligned on that target port.
Makes perfect sense.
It's also worth noting that a cluster IP isn't a real IP on a physical network interface. It's a virtual IP, managed entirely by kubeproxy writing imptables, or IPZS rules, on every node to intercept the traffic.
It definitely forces you to understand the traffic flow. But if we zoom out a bit, cluster IP has a pretty glaring limitation.
Which is?
If everything is completely locked down and isolated inside the cluster, how do actual users on the internet access the application? I mean, a cluster where everything is completely isolated from the outside world isn't very useful for a public-facing e-commerce site.
Right. You need a way to open the gates.
Exactly.
So let external internet traffic in, we move to the external service types. And the foundational one there is called NodePort.
So how does NodePort pierce that internal boundary compared to a cluster IP?
It actually builds right on top of it.
Yeah.
When you define a service as type NodePort, Kubernetes still provisions that internal virtual cluster IP. But then it takes an extra step. It opens a specific static port on the IP address of every single worker node in your entire cluster.
Wait, every single node. If you are running a massive 100-node cluster, that port is blasted open on all 100 machines.
All 100 of them.
Wow.
Yeah, and to prevent this from clashing with standard system processes running on those nodes, Kubernetes forces you to use a very specific high-numbered port range. It restricts node port assignments to the range of 30,000 to 327677.
Ah, okay.
So in your manifest, you change type to node port, and you can optionally specify a field like NodePort :300880.
So external traffic can hit the public IP of literally any node in my cluster on port 3080. And the internal proxy network, kube proxy, will grab that traffic, route it to the service, and the service drops it to a healthy pod.
That's exactly how it works.
Even if the node that received the external request doesn't actually have a pod for that application running on it, like it just forwards it across the cluster network to a node that does.
Yep, that cross-node routing happens instantly behind the scenes.
Okay, let me play devil's advocate here for a second, because this sounds wildly impractical for a real business. If it forces you to use these strange high port numbers like 380, why would anyone ever use a node port in production? I mean, nobody is going to tell their customers, hey, check out our new web store at our IP address, :380.
Definitely not.
It looks suspicious, and corporate firewalls will just block it. Why not just use the next type, the load balancer, every single time to get a clean entry point?
Well, cost and environment constraints dictate that choice. Load balancer is absolutely the polished, production-ready solution for public-facing apps. When you set type load balancer, Kubernetes talks directly to your cloud provider's API, AWS, Google Cloud, Azure, and tells it to automatically spin up a dedicated external load balancer.
Right.
That piece of cloud infrastructure gets a standard public IP, listens on a clean port 80 or 443, and routes traffic down into your cluster's node ports.
Which sounds exactly like what you would want for a real website.
It is, but cloud load balancers cost real money.
Yeah.
Every single time you create a load balancer service, your cloud provider starts a meter.
Oh, I see.
If you have a microservice architecture with 50 different public-facing APIs, and you make them all load balancers, your monthly cloud bill is going to be astronomical.
Ouch. Plus, I guess there is the environment constraint. What if you are not running in the cloud?
Exactly.
Like if I am doing local development on my laptop using Minikube, or if I used Cube ADM to bootstrap a bare metal cluster on some physical servers in a local data center, I don't have an AWS API to call.
Right. The cluster literally lacks the cloud controller manager needed to provision external hardware.
Makes sense.
In those bare metal scenarios, or in highly cost-constrained environments, NodePort is your universal infrastructure agnostic fallback. It works anywhere instantly without relying on third-party cloud integrations.
So you just build around it.
Yeah, you might deploy your own open source proxy like Hey Proxy or Nginx in front of those node ports to clean up the URLs and terminate SSL for your users. But the node port itself is the underlying mechanism getting the traffic into the cluster.
Okay, so NodePort is the universal adapter, and Load Balancer is the polished cloud integration that you pay for.
You got it.
Both of them, along with ClusterIP, are fundamentally doing load balancing. They take incoming traffic and distribute it across a pool of pods. But what if you don't want Kubernetes to do that?
What do you mean?
Like, what if you need to talk to a specific pod, not just any random replica?
Oh, right. A classic example of this requirement is a stateful application. If you are running a database cluster using a stateful set, say a primary node for writing data and several replica nodes for reading data, you can't just send a database write query to a random load balanced pod.
Yeah, it has to go directly to the primary node.
Right.
Because if you write user data to a read-only replica by mistake, the database throws an error and the transaction just fails.
Right.
So how do we bypass the load balancer but still use a service to dynamically find the pods?
We use a headless service. Yeah, you configure this by explicitly setting ClusterIP:"none" in your YAML manifest. When Kubernetes sees that none value, it skips allocating a virtual proxy IP entirely. It turns off the internal load balancing.
So what does it do instead? If a client application queries the service, what actually comes back?
It leverages the internal cluster DNS. When your front end queries the DNS name of a headless service, the DNS server doesn't return a single virtual IP. It returns multiple A or AAA records.
Oh, wow.
Yeah, it hands you the actual direct IP addresses of every individual healthy pod that matches the selector.
I like to think of this like calling a company switchboard. A standard ClusterIP service is when you call the main number and the receptionist routes you to the next available agent. You have no idea who you were going to talk to.
Exactly.
But a headless service is like calling that same receptionist and saying, don't transfer me. Read me the direct phone extensions of every single person currently working in the department.
I love that. And then you, the client application, take that list of extensions and decide exactly who to dial. The application implements its own client-side routing logic, maybe using a framework like gRPC round robin or ribbon, to figure out which pod is the primary and connects directly to it.
Okay, so we have completely solved routing inside the cluster and getting traffic into the cluster. But here's a curveball for you.
Hit me.
What if you are migrating a legacy application and your main database is still sitting on an old physical server outside the cluster? Can a service help your pods talk to the outside world without hard-coding the external IP in the application config.
Yes, actually, using a completely different service type called external name.
Okay.
This one doesn't have a selector at all, and it doesn't use network ports. You just give it an external name field, like legacy-db.mycompany.com.
Oh, so it just acts as a DNS alias. It maps the internal Kubernetes service name to that external DNS name using a CNME record?
That is exactly how it functions. You create an external name service called MyDatabase inside the cluster. Your pods just connect to the hostname MyDatabase. The cluster DNS resolves it, returns the CNME, and seamlessly directs the traffic to the external legacy server.
Man, that is a massive operational win.
Huge win.
Because, 6 months down the line, when you finally migrate that legacy database into the Kubernetes cluster, you don't have to touch your application code. You just change the service type from external name to cluster IP, add a selector, and suddenly the traffic routes internally.
Yep, the application developers are completely shielded from the infrastructure migration.
That pure abstraction is why services are so heavily utilized. And you mentioned DNS a moment ago. The internal DNS is basically the absolute backbone of all this routing.
Oh, 100%.
Yeah.
The cluster runs a DNS service, almost universally core DNS these days, which constantly watches the Kube API. When you create a service, core DNS instantly generates and caches DNS records for it.
Right. And if you are writing application code or configuring a connection string, you really need to know the exact format of that DNS name.
Yes, the fully qualified domain name, or FQDN, follows a very strict pattern. It's servicename.namespace.svc.cluster.local.
So if you have a service named auth backend in a namespace called production, the full DNS address is authbackend.production.svc.cluster.local.
Exactly. The SVC indicates it is a service, and cluster.local is the default root domain for the entire cluster.
And if my front-end web app is running in that exact same production namespace, I can just use the short name authbackend, right?
Right. Core DNS is smart enough to append the local namespace search domains.
But if my front end is in a staging namespace trying to reach the production namespace, then I have to use the full domain name to bridge that gap.
You do. And the pods themselves get DNS names too, which is crucial for those headless services we just discussed. A pod's DNS name just replaces the dots in its IP address with dashes.
Oh, interesting.
So an IP of 10.244.1.5 becomes 10-244-1.5.namespace.pod.cluster.local. etcd holds all this state securely, and core DNS serves it up dynamically.
Let's bring this down to the practitioner level for a second. If you are deep in the terminal troubleshooting an outage, you don't always want to write 20 lines of YAML just to test basic connectivity.
Definitely not.
You can use imperative commands. If I have a deployment named nginx, I can just type kubectl expose deployment nginx -- port equals 80 -- type equals NodePort.
It is incredibly fast for rapid testing. That command automatically creates the service, sets the type, and dynamically builds the selector to perfectly match the labels on your nginx deployment.
Nice.
But creation is only half the battle. Troubleshooting is where engineers spend most of their time.
Which brings us to verifying where the traffic is actually going. If a front end is timing out trying to reach the back end, your first step isn't checking the application logs of the front end.
No, your first step is checking if the service actually found the back-end pods.
Right. So if you run kubectl get endpoints my service, I am assuming you should see a list of actual pod IP addresses.
You should definitely see a populated list. That endpoints object is the dynamic list of healthy pod IPs the service compiled. If you see IPs there, your labels and selectors are working perfectly.
But if you run kubectl get endpoints and that list is completely blank or it says none, you know your service is essentially a bridge to nowhere. The service exists, it is listening for traffic, but it hasn't mapped to a single pod.
Exactly. And 9 times out of 10, that means you have a typo in your labels. Your deployment manifest says app:/myapp with a dash, and your service selector says app:/myapp without a dash.
Such a common mistake.
To fix it, you just run kubectl, get pods -- show labels, cross-reference the output with your service manifest, and fix the mismatch. The second you apply the fix, the Kube API registers the change, and the endpoints will automatically populate.
That is a golden troubleshooting workflow right there. Check the endpoints first. Well, we have covered a massive amount of ground today.
It really have.
We started with the sheer chaos of ephemeral pods and how the Kubernetes service acts as the anchor, the order window, abstracting that chaos away using labels and selectors. We looked at ClusterIP for internal isolation and opened the gates with NodePort and Load Balancer for external traffic.
We bypassed load balancing entirely with headless services for stateful apps and mapped external legacy infrastructure with external name.
And tied it all together with CoordNS and the kubectl commands you need to expose resources and verify that those crucial endpoints are actually routing traffic.
It's a lot, but it's essential.
It is. Understanding these service types is the foundation of cloud-native networking. It is the difference between building a fragile system that crumbles during a node failure and an architecture that heals itself while you sleep. But as powerful as all of this is, it feels like we are still just pushing packets around based on IP addresses and basic ports.
We are, and that leads perfectly into a provocative thought to leave you with today.
Oh, let's hear it.
The source material points toward a massive evolution in Kubernetes networking. The services and ingress controllers we discussed today operate primarily at layer 4 of the networking stack. They just manage IPs and ports. But the ecosystem is actively moving towards something called the Gateway API.
The Gateway API. So we are moving up the stack.
We are moving to layer 7. The Gateway API is a highly protocol-aware, role-oriented extension. It offers advanced dynamic traffic routing that traditional services simply cannot do natively.
Like what kind of routing?
We are talking about native support for HTTP, header-based matching, complex traffic waiting for canary deployments, and granular role separations between the platform engineers managing the infrastructure and the developers writing the apps.
Wow. So we are taking that simple order window concept and upgrading it into an intelligent, programmable logistics center that actually looks at the contents of the tickets before routing them.
That is exactly it. It's the future of cluster ingress. So look at your current architecture. Are you relying on a tangled mess of basic node ports and complex ingress annotations just to route your HTTP traffic?
Probably, yeah.
As your application scales in complexity, it might be time to ask yourself if you need to evolve beyond the limitations of basic layer 4 services and explore what the Gateway API can unlock for your routing logic.
That is definitely a paradigm shift worth exploring on your own. It completely changes how we handle traffic. Well, thank you for diving into the muddy, complex, but ultimately beautiful world of Kubernetes networking with us today. Until next time.